Hi, folks. It's 2:30, and today's lecture is going to be LLMs. I'll be giving you guys a brief primer on how LLMs came about, um, language modeling, natural language processing, and then finally a brief overview of how ChatGPT was originally structured. So, like ChatGPT 2, 3, 3.0 was structured, but by the time 4 and 5 came out, the structures have changed, the transformers background has changed. So I won't be going into that detail. I'll also give you a couple of links onto Andrei Karpathy's NanoGPT project, which if you want to like create your own ChatGPT version, NanoGPT is really good at that. So you can just take any corpus of any text that you have, and it can create a language model for you. But today's lecture is primarily going to be based on the fundamentals of language modeling, natural language processing, and then moving on to the fundamentals of large language models and why they're large, and what goes into building them, how they respond, and where they fail, essentially. This is going to be, I don't think you have an assignment or any exams on any of this. So this is purely for your understanding. And for if you want to build on this in the future, you're computer scientists, so you have to understand what this tech is, how this tech is being built, right? So like I said, first I'll focus on natural language modeling because that was where LLMs came out of, language models, and then I'll be talking about what the fundamental ChatGPT architecture is and the difficulties of aligning it to to any purpose whatsoever. And I'll mostly be focusing on the single modality. That modality is just text. But modern LLMs, as you know, are multimodal. So they work with your screens, with images, with text, with audio, everything. But this lecture is going to be focused on the single modality, which was the original modality of LLMs, which is text. So before any of this came along, one of the fundamental purposes of computer science has always been understanding languages, decoding languages, and getting meaning out of it. Even in the 40s and 50s, during the World War and during early Cold War period, a lot of computational resources was spent on decoding what people were saying up on the radio waves, what early scanning things were going on, what was being set up on telegraphs and wires and so on and so forth. That evolved into understanding that we can't do this kind of task piecemeal. So we have to go back into the fundamentals, and the fundamentals is understanding how humans speak to each other, like understanding how languages work, right? And that's not easy. We have, as humans, we have a lot of context around how language works that a computer does just as not. Like when I'm the words that I'm speaking to you right now make perfect sense to you, but wouldn't have made perfect sense to people 500 years back during Shakespeare's period, or it might not make perfect sense to people 500 years from now. So language is very, very contextual, right? And so before this kind of stuff could be done, we had to build up. Computer scientists had to build up this field from the ground up, called the natural language processing, right? So natural language processing falls under computer science, falls under AI, falls under computational linguistics, CL, and it is a hard challenge. Even though these days it seems very, very simple because of how large language models have evolved, it wasn't. Even 10 years back, it was considered one of the most challenging things. So humans rely on like lots of implicit references, memory, colloquialisms that are not easily understandable without giving a model extreme amounts of data, right? So for a model to understand everything like thoroughly, it has to understand everything about the world, which is fundamentally fairly difficult, right? So the ultimate goal of any of this was very natural interaction between humans and computers, so that humans can communicate with other humans much more easily if we are able to communicate with computers easily. Now, this became very recently, over the last 5 years, this has become more or less a solved problem, right? Your computers, especially large language models, are able to understand us much, much better than they were able to understand us like 10, 15 years ago. Like this is an example I just picked up from Twitter, where somebody was telling a ChatGPT thing just very colloquially, in the way that normal humans would speak to each other, telling ChatGPT to follow rules, to follow instructions, and ChatGPT was able to follow them. Right? Like the original purpose of the Turing test has been solved. But this is not what the end goal of natural language processing is. Natural language processing works on all the different texts that the internet generates, that human commerce generates. So it has to be able to understand, say, for example, email spam. It has to be able to understand what people are buying and selling for advertisement purposes. It has to be able to understand, say, for example, what a doctor's prescription is telling you. It has to be able to understand what the safety data sheet of a chemical is, so that you're able to so that the model is able to accurately guide a person in a chemical plant, right? So all these separate things have to be solved individually before a general purpose solution can be created, right? So these are various images that I just picked up of the internet of like where natural language modeling 10, 15 years ago was being mostly used, right? Emails, machine translation. Obviously, translation is something I forgot. Translation is one of the big challenges of natural language modeling. But again, it is a solved problem, translation, for the commonly spoken languages, right? The LLMs that I'm talking about today are mostly focused around English, and the big LLMs today are all focused around English and Mandarin. But LLMs, there's no reason for an LLM to be stuck with those languages, right? They work with Spanish, they work with German, they work with Russian, they work with all the subcontinental languages, and so machine translation between languages is now more or less automatic. But again, there are challenges that I'll talk about later. Sentiment analysis, you will find like even as the LLMs were coming out like 2, 3 years back, like around the COVID period, you will find an explosion of papers doing sentiment analysis. Whether they're doing sentiment analysis on like Twitter posts, whether they're doing sentiment analysis on like news reports, on this kind of stuff, which is like consumer reports, consumer reviews, and things like that. This is no longer as big a thing as it used to be because LLMs can do this whole thing for you much faster and much more accurate than like piecemeal models used to be able to do. But like sentiment analysis was a big deal, and now that field is kind of under control. Information extraction is what I was talking about. So if you have safety data sheets, if you have daily reviews, if you have daily performance reviews, and you want a machine to go through all the text that is being generated in a normal business, like day to day, a business generates like tens of thousands of words of text, and you want a machine to go through them instead of having a person, instead of having a secretary go through them. A machine might, a natural language model might go through them and pick out what's important, right? It might this didn't used to be a good thing because it used to fail more often than not. But again, the balance has changed over the last few years or so. And information extraction is one of the things that LLMs are generally very good at, generally, because there are obviously edge cases. If you're one of the edge cases that I think I'll talk about today is that LLMs have contextual memory. So LLMs can remember, say, for example, 10,000 words, 15,000 words very well. But if you give an LLM a bigger report, if you give a million word document for an LLM to peruse, it's going to forget what happened 100,000 years ago, words ago, and it's not going to tell you what it forgot. It's just going to make things up. So that's one of the challenges of of aligning a large language model. And a big problem these days have been initially it was not a problem. Initially it was considered a really good thing. Is text generation. Right. People have tested this out where they were generating text using language models before even large language models came out, and they were sending it for publications, and people would get fooled, and people would accept these like nonsensical papers. That happens a lot more these days. If any of you are submitting papers to NIPS or ICLR or any of the big AI conferences, big AI publications, journals, or whatever, you will see that they're going to tell you that the volume of papers submitted to these big journals, ICLR, NIPS, whatever, any of the IEEE journals, the volume has gone up by 10, 20, 30 times. Where they used to get 500, 600 submissions, and where they would accept 20 of them. Now the submission rates have gone up to 10,000, 15,000. And a lot of it is like, if it's not entirely generated by an LLM, partially generated by an LLM. And again, a human has to go through and also solve it. So all of this is to tell you like, why is natural language processing hard? Well, the first thing is like all these implicit things, right? What people mean when they say when they say certain words, what people mean in words have different meaning in different contexts, right? And a language model has to understand that context without it being told explicitly what the context is, because a human doesn't need to be told what the context is every single time, but a language model needed to be told. So that is one of the major challenges. So uh, contextual things like this, like you have a paragraph. This is considered one of the fundamental problems of NLP. If you have taken an NLP class before, you have probably seen this paragraph, and your model has been asked to decode this paragraph, right? So if you give an LLM a paragraph like this, and you ask questions like those that are written, who wrote Winnie the Pooh? Where did Chris live? All that information is in the paragraphs, but that all this information is very contextual. Like it depends upon parts of speech tagging. It depends upon how sentences are constructed in English language. All of these things, right? Like whenever his father, him, what are these references to? And this is just a single paragraph. And if you have like major thousands and thousands of words, it has to be understood. It's not easy. Uh, Tagging this, following this along, it's not easy. And that is one of the challenges that had to be solved. And the other major problem that NLP faced was the problem of scale, right? If you want a natural language model to understand what a human is saying, you have to essentially give it all the possible context and all the possible text that a human might have listened to over their entire life, right? And mostly, even though that sounds impossible, modern LLMs have done that. They have gone through essentially the entirety of the internet and put it into their corpus and trained their models on top of it. That's why modern models can have, like you see the Bible has like 700,000 words. A bank information has like 1 million words. Newswire collection, newspaper reports have 500 million plus words, etc., etc. And the models that have been created based on this, all the LLM models, they have billions and trillions of tokens in them to understand all of these languages. So essentially, the way we solve this is by brute forcing. Like we've created models large enough that essentially the entirety of human information is somehow compressed and stored within it. That's how we ended up solving this problem. The other thing is language is dynamic because language changes, right? Like I talked to my friends on Discord and I picked up like 10 of the like acronyms, slangs, whatever you call them. I don't know what they're like. What is the language theoretic word for things like NPCs and FR for you, Riz, whatever. Doesn't matter. The point is like these things, they have meaning today. They might not have had the exact same meanings 10 years ago, right? 15 years ago. So if you're scanning through a text, say from 1995, then some of these words may appear in them, but they're going to have different meaning if you than a text that is written today, right? So language is very dynamic, and there is no cutoff lines like that. You can say like, okay, this word before 2005 means something else, and after 2005 means something. So this has to be done dynamically, the way humans do it. And language is also compositional. So individual words, this wet floor caution, wet floor sign in Mandarin. Um, Individual logograms mean different thing versus the entire logogram put together, right? I hope this is correct because I picked this up from the internet. But what different things mean is that they can be translated differently based on how different words are placed next to each other, right? So this is not just dynamism, this is also composition. Like the way you are placing different words together means very different things. Like this is very fundamental to humans, right? But it is difficult to make a machine understand this. So a couple of like 5 or 6 different terms that are very common in natural language processing, that if you're creating your own LLM or whatever, these words are going to come up with like lots of times, like morphology, lexicography, syntax, syntactical reasoning, semantical reasoning, discourse, all of these things, like they come up of very often. So that's why I have them here so that you can just take a look at what it means when they're going to pop up in an LLM, right? What is semantics? What is discourse, etc., etc. So following semantic meaning over lines over different sentences, so on and so forth. So to solve this problem, what we initially had were two different categories of language models, right? The first is statistical models. So if you have heard of BERT, etc., those used to be statistical models. And today what we have, statistical models were reversible uh, and you understandable, essentially, completely explainable. That's what statistical language models used to be. They used to statistical language models were very powerful when used for decoding. Say, for example, in World War II, if when the English were trying to decode German transmissions or whatever, they were using statistical language models because they knew certain words popped up in certain different positions. So if somebody was talking to if a ship commander was reporting back to headquarters or whatever, they had fixed things that they were saying at the start of a sentence and at the end of a sentence, like hello or good morning or hi or whatever, and then thank you at the end. So that kind of statistical patterns, natural language modeling were like fundamentally relied on for a very long time, right? When neural language models came in, we were essentially doing the same thing, but all those patterns were being discovered by neural net, essentially. Like I said, like a month ago, neural network is a universal approximator. So it was essentially approximating the function of a human language, essentially. And it was big neural models were trained on huge corpuses of text. The Nano GPT by Andrei Karpathy that I'll link to at the end, you can train it on Shakespeare, for example, and it's going to give you very Shakespearean language because that's what our natural language model learns, right? And a very important part of this kind of neural language models is that it doesn't lose rare words. So if a word only appears like 5 times out of a 500 million word corpus, it's not going to forget it, which happens in statistical models where outliers are essentially, they get discarded. But neural models, they have those stored in their, essentially in their neurons. And they're able to capture them, they're able to capture context, they're able to handle very complex interactions between languages, and these were slowly solved. These were not solved in one go, but they were slowly solved as we develop more and more powerful natural language models. Originally, NLPs natural language processing used recurrent neural networks, long short-term memory, LSTM architecture, et cetera. But these days, almost every single natural language model that you will use, large language model that you use, is based on some form of transformer architecture or attention-based transformer architecture, which I'll talk about what they are later. Recurrent models or older recurrent models require lots of sequential computations, which are not good for GPUs. And a lot of those could not be reparameterized. Like I said in the diffusion model lecture, when you move forward by adding noise and then you move backward by extracting meaning from noise, in a diffusion model, the reparameterization trick essentially allows you to skip all the steps and go directly to the solution. From the noise, you go to the recreated image directly in one step. That was hard to do for a natural language model. Um, so transformers is the architecture that essentially has taken over like modern deep learning, modern machine learning, right? Recurrent neural networks, long short-term memories, GRUs, where the architecture that we use for NLPs. Before that, you can add in attention mechanism to recurrent neural networks. and also to like reinforcement learning networks, even though it gets more complicated. But the major problem is that before transformers, all RNNs, etc., they used to take in words as they came in, right? So they were always sequential. They were always first in, last out, right? So they were all of this was sequential, and that is a major problem for languages, right? Because even though we speak sequentially, meaning does not flow sequentially through a language. So the transformer architecture essentially solved this problem, and by essentially making sure that you listen to older words as well. So if you have a sentence coming in, the last word is not the word that is most important. You listen to the previous words before that as well, which again sounds very obvious, but it's kind of hard to do mathematically. Like how do you give this weight, right? That's what the attention mechanism. The all you need is attention paper essentially like changed the fundamental structure of modern deep learning essentially through that. So original NLPs moved to language models, moved to large language models. So this was the original structure of older NLPs. It's no longer, I mean, this is pretty much not used at all these days. Then we moved to language models, BERT, Roberta, Electra, all the different models like that, and the encoder decoder models. You can see an example of BERT here. You'll find papers published on BERT even to this day, but it is essentially being slowly pushed over by large language models. And from these, we move to very large language models. So these have trillions and billions of parameters while they were doing constructing. So these are some of the largest ones. I tried to put in here some of the lesser known ones, but still huge ones, because Claude isn't here, Anthropix Claude isn't here, Gemini isn't here, Llama isn't here, ChatGPT. Oh no, Llama is here. ChatGPT isn't here. But these are all other fairly large models. But this image is already out of date because Qwen 3 is already out of date. DeepSeek version 3 is already out of date because they have come up with a new architecture. So this field, everything I tell you in this field is probably out of date as I'm telling you this. So that's why I'm telling you the fundamentals of how this works. So this is an example of what outputs used to look like, large language models outputs used to look like. This is 6 years ago. This is in 2019. What's up?
So my last slide, we were talking about architecture. Are there any like large language models that are completely linear, or do they all have like a horizontal flow?
No, modern large language models are not linear. The essentially the fundamentals of the transformer architecture that I told you, it makes it not. I mean, it doesn't. That sequential thing no longer applies. You can essentially take it one word at a time and make it fully sequential, but again, you're going to lose all that power that this gives you, that this transformer attention mechanism gives you to do it that way. But again, this is a developing field. You never know. 5 years from now, someone might come up with an architecture that like completely changes it all over again. Like 5 years ago, this didn't exist. 5 years from now, it might not exist again. Yeah, like I said, like this is the same question 3 years ago. So this is 6 years ago. You ask a question like, what concepts should I cover in a presentation on LLMs? So it's a very like the answer is not very detailed, right? It's a very generic statement that somebody who doesn't really know the topic would give you, right? This is GPT-2. This is GPT 3.5. Already you can see where's the isn't there a zoom thing? Yeah. So already you can see that this result from 2022 is far more like complex. Like it has actual meaning, right? This is not meaningless essentially, which as opposed to oh my god, this I have no idea what happened there. This took me back all the way. Yeah, as opposed to this one, which is a very generic statement. This already has meaning. right? But compare this from 3 years ago to this result, which I created this morning, right? So as you can already see how much more detail there is, right? Like this is so much more detailed uh, compared to even yesterday's 3 years ago, right? But another major problem is that uh, especially OpenAI and Sam Altman and ChatGPT and all of them, they don't have a path forward from this, right? Like this result is pretty much identical to the result you'd have gotten 6 months ago. So this field is already kind of stagnating, right? So again, this is something that you as computer scientists are going to have to find some method of solving. So now we follow like the ChatGPT architecture, right? So this is how ChatGPT works essentially, and this is the full structure of a large language model today. Um, at very high level, I'll go into detail after this, is a transformer-based large language model is an autoregressive next token predictor. What that means is that essentially it's a Markov model, right? You give it a set of tokens, it's going to predict what the next token is going to be to that. So if you have, I mean, all of you have done supervised learning, all of you have done Gaussian modeling, et cetera, et cetera. This is a very linear version of that, right? It compresses the a Gaussian modeling system or a supervised learning system into one dimension, and that one dimension is just the next token, right? So it has simplified a fairly large thing into one. It's the token that I mean, embeddings, tokens, all of these have different meanings, but you can call it a token. So the tokens are the inputs to the text, and as you give it words, it's going to predict what the next token should be, and that works on its generated tokens as well. So as it's creating a solution, as it's creating a token out of it, that token is also part of what it's going to generate next. So the generated tokens are not independent of themselves. These generated tokens are essentially sampled from a probability distribution. That sample is like the sample that it takes is the next token, the way diffusion models work as well. This newly selected token is appended to the sequence and the process is repeated. So it's a very, very simple group once you think about it. So how does that loop work in practice? So there's essentially three steps, right? The first is the transformer-based architecture of the large language model. This is different for different models. I'm showing you the ChatGPT version, but DeepSeek, Claude, Anthropic's Claude, Gemini, Llama, all of them have slightly different architectures, have slightly different training processes. So first you use that, then you do the pre-training, then you do SFT. SFT stands for supervised fine-tuning. And finally, you do the human part of it, which is RLHF, which is reinforcement learning from human feedback. So these are essentially the three steps. You do the pre-training part using all the text that's in the internet, put it into your language model, see what it spits out. Then you do some supervised fine-tuning on it, and then you bring in a human to see what the output of that model is and correct it based on that, right? So the first step is the transformers, right? So modern, like I said, modern language models use the transformer architecture. This lecture is not going to go into detail on the transformer architecture. It's like this is like essentially an entire graduate course on its own. But what I'll tell you, this is an overview of it. There's essentially two parts, the encoder and the decoder. But modern large language models don't use both parts. They don't have an encoder decoder version. LLMs are decoder only, right? All they need is the decoder part. So let's see how the model's input is constructed, right? So this transformer that I just showed, this transformer that I just showed, takes raw text as input and it embeds all of those raw text into tokens. So let's say your raw text is LLMs are cool. So then it tokenizes it, right? It takes all the individual parts of this sentence, breaks it up into tokens. Uh, And how this is tokenized is one of the formula for Pepsi or whatever. So different models, ChatGPT does it differently, Llama does it differently. So exactly how this is tokenized is going to improve or kill your LLM essentially. And this is for English language. For say, for example, for Mandarin, it works very differently. Individual logograms, like you don't one logogram is not one token. It's broken down into further stuff. So first we convert this text into a sequence of tokens, then we convert this into a sequence of vectors, right? So because this is all of the these things like this is essentially what it is doing is it's doing parts of speech tagging. So what are nouns? What are apostrophes? What are prepositions? All of the like it doesn't know these terms for the text. The transformer doesn't know what are nouns, what are things like that. What it does know is associations. So how are nouns associated with each other? How are adverbs associated with each other? All these different parts of the speech are being tagged together into this embedding layer, right? And this final thing that you see, this parts of speech tagged token set, this is what goes into the input of the transformer, right? Um, the original transformer layer that I showed you, the inputs are lists of vectors, outputs are another list of vectors, so that essentially they chain each other, right? The tokens follow each other. So the each block transforms these vectors. um, so this is where the attention mechanism that I told you about comes in. So all these, what this does is, uh, whenever 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 you have an output, the output is not just looking at the first word that is being sent as input. Um, it is also looking at the previous words. It is also looking at preceding tokens. So the second output token is going to look at the first two input tokens. The third is going to look at the first three input tokens, etc., etc. So this is how essentially the masked self-attention thing continues. And each of these individual outputs, these are coming in through the neural network, through the entire transformer architecture. So it is taking all of these things as input to a neural network. Right. And this is being transformed. Each token is being individually transformed and recreated to get the output. Right. This is how the decoder or the transformer layer kind of works. And we do it many times. We stack this process, we stack it over and over and over and over again. And that's why that's how these models are stored as well. And that's what it means when it says like some model has 300 billion parameters, some model has 1 trillion parameters. So these blocks are what we are talking about. And then we do layer normalization, we feed forward transformation. There's a lot of like mechanistic, probabilistic things that happen on top of this. I'm not going into all of them because that's not necessary. What I wanted to show you is that when an LLM, when ChatGPT generates a single output, it looks at like 4, 5, 6 different tokens that came before the current output. And each of those tokens that are being generated come in through an entire feed-forward mechanism, come in through an entire neural network. Uh, so essentially, think of it as like a large neural network that is being constructed for the first word. It's a one word, one input neural network. Second word, two input neural network, and so on and so forth. That's what it's doing. That's the decoder only architecture. After this part is called like this whole section is called the pre-training part. Now, the objective of this neural network, or the objective of all large language models, is to predict the next token and what next token is the most accurate version, a Markov chain, essentially. So you start with unlabeled text, so like the entire set of the Wikipedia textual corpus. You sample any one part of it. You take one sentence from a Wikipedia article, and then you put it into your decoder-only architecture, see what token it spits out of it, and then check to see whether it matches the original text or not. Right. So this is how. Did I miss something? Yeah. Sorry. Yeah. This is how the decoder-only architecture is pre-trained. What's up?
So the way you described it, of like kind of like looking at the first word and passing that through the neural network, making prediction, then doing that for even 2 words, and then just like keep increasing. That really helped understand. But I'm wondering what would be in this analogy, like what would be the output of that?
The output is just another token. So like you give it like in this case, for example, like this is a kind of sample input that goes in. Like you give it a sentence, like what is the date of the American independence, right? You give it a sentence like this, so it processes them step by step. What is the date, so on and so forth. So it processes all of them, and then when it gets to the when it gets to the end of it, and when it's time for the first token to be generated, like the answer to be generated, it doesn't just look at the final word of the sentence. The final word of the sentence is just a question mark, right? It looks at all those previous words that I said. So what is the date of the American independence? It looks at the question mark, it looks at the independence, it looks at American, looks at all of them to generate the next word.
Right. So then the output
Is the answer.
Is the next expected word.
Yes. What would in a general text, in any text, what would the next word out after a question like that would be? So that's what it predicts, essentially. That's why training it on text like Wikipedia is so good, because it generally, those are declarative statements, and it's much easier for an LLM to work on scientific papers, Wikipedia, etc., etc. If you have, say, for example, one of the ways of, like, I first tested out large language models was that if you have a Discord server or a Telegram server or anything like that, you train a language model on all the text in a particular channel in a server. And then you give it a name of a person in that channel, and that whatever it generates, you'll find that it's able to capture a person, how a person speaks, right? It's eerily accurate, especially modern language models. It's even 5 years ago it was powerful, and these days it's impossible for you to tell whether you really said something or you didn't say it, right? That's how powerful the prediction part has gotten to be. The labels in self-supervised is presented in the data itself. The way we train it is train it over essentially at this point all the text available on the internet, right? And this pre-training is very expensive. It takes months for a new model of, say, for example, training ChatGPT 5.0 to, like I said, it took months, 3 to 4 weeks, right? And another, like, ethical problem comes up here is that if you are scraping all the work from the internet, you're not paying anyone because it's already on the internet. Is it ethical to do that? Is it a good idea to take text that someone has not given you permission to scrape and use it to train your model? I mean, it's a moot question now because they've already all done it. Like, it's once you've done it, there's no way to stop it. But again, it's a moral and ethical question if they should continue doing this going forward. Right? And the self-supervised learning part, what it does is that it does this training. So it takes all of these tokens that are being generated, compares it to the original text of the internet, and then it checks whether the probability of it generating the correct text after a sentence, the correct token after an input token, whether it matches the original input data or not. And if it doesn't, you retrain it like a normal neural network. So this is how the text generation part of a next token prediction model works. So you are given a sequence of tokens as input, you predict the next token, then you add it to the input sequence, and then you repeat it. Right? That's all there is to it. It's It's fairly simple, but in practice, implementing it is kind of hard because how long this context window should be is essentially we don't know. Like you create an LLM on your own computer, even at 10-word context window, sometimes it's like too much for your model to handle. Modern ChatGPT can do 100,000 words, but even that's not enough because sometimes you need to keep like millions of words uh, in mind. So the way these models have gotten more and more successful is not just this transformer architecture, this masked self-attention transformer architecture. It's also because the models have gotten exceptionally large, and modern GPU architectures have gotten really good at parallelizing this kind of transformer architecture and pre-training uh, this kind of information. So you can see how much floating point operations per second you need to train to train these models, right? Like this is from 2022, and you can already see how big these models are. They have 280 billion tokens. The Gopher model, the Chinchilla model, which was very famous in 2022 because it was very efficient, and it's now completely outclassed. The 2022 Chinchilla model, it performs worse than even the smallest model of 2025. So again, the way this was solved is by brute forcing it, essentially giving it all the information that you can. This is a slightly more modern architecture diagram. So you can see how huge these models have gotten. That's what, uh, well, this is what you're competing with if you're creating your own large language models these days. The final step of these token generation process is alignment. So what alignment means is that aligning the output of the large language model to something a human understands, right? To make it human readable, make it human observable, and to be able to fool a human, essentially, to be able to pass the Turing test. That's what the alignment process is. Like what it gives you exactly what you are asking it. Now the alignment process is it's kind of like magic trick. Like there's no fixed guaranteed methods that if you align it this way, it's going to perform well. It's all people are still experimenting on how this is being done. But generally, the criteria for a good alignment is these four things. You must follow the instructions that are given within the text itself. So if it's telling you to stop predicting tokens after a certain point, you should stop predicting tokens after that point. Don't hallucinate, which is obvious, which is a problem I think we've all seen. Be more interesting, which is don't fall into the mode collapse trap, where all you are generating, no matter what input you're getting, giving the model is generating the same boring text essentially, right? And like, what else is there? Like that's up to you, right? Uh, uh, Aligning a large language model is an open problem. A lot of papers have been published, even to this day, is like how exactly do you accurately align it? How do you judge whether a model has been perfectly aligned, whether it's giving you exactly the results that you want or not? How do you break the model essentially? So again, these are open questions, and as computer scientists, these are things that you have to solve. So the two main things that ChatGPT does to solve this alignment process is SFT and RLHF. So SFT means supervised fine tuning, and RLHF, like I said, means reinforcement learning from human feedback. Right? So what is supervised fine tuning? We continue to use this next token prediction, but it is applied over focused information. So it looks at sessions from other LLMs. It looks at like if you generate text that has followed the examples, followed your instructions. So you give it text where it says that LLM do this and then stop. And then the answer is like it has done that and stopped. And you give that as input to your LLMs. You give it very accurate prompt response pairs. So you give it a question and an answer, question, answer, question, answer. And these are all completely accurate. So it learns to model this structure. It used to be before like modern GPT, It used to be that every time to get good results from a large language models, you would always have token indicators, tone indicators at the start of the text that you'll be giving. So you'll be giving it like within bracket question and then your question. And then you give it within brackets answer. And then it would generate the answer because it recognizes that pattern, essentially. Modern LLMs don't really care. They have understood all of that very well. And the most important thing is where computer scientists come in is domain-specific data. So, for example, if you have like a huge, if you are, say, for example, a big company like your Salesforce or Accenture or whatever, one of those big IT companies, and you're working with some domain-specific company, some chemical company or whatever, they have lots and thousands of pages of internal literature, right? Internal literature on how some machines work, how processes work, how safety works, etc., etc. So if you train a general purpose LLM on that data, um, it is very likely that if you ask that LLM a question, it's not going to look at the data from that company. It's just going to look at the information that it has, like generic information, and it's going to answer based on that. So what you have to do, what supervised fine tuning has to do, is make sure that when a targeted question is asked, the answer to that question comes from the text, from the information of that company itself. That's kind of, it's not easy. That's not easy to do. This kind of fine tuning, if you do it too much, then it loses generalizability. Like it loses what makes LLMs powerful. Like this, like natural language responses. So there's a very narrow window. There are several very narrow windows where fine tuning on a particular data set is good for an LLM. But if you move out of that window, it's bad. And this is something computer scientists have to figure out. What there's no like perfect answer for how this alignment is good or bad. The other is reinforcement learning from human feedback. This was more common in the early days of GPTs, where you go into Amazon Mechanical Turk or all of those different captchas, like thousands and thousands of different captchas that you had to click through when you were opening a website, where it would tell you like, okay, what does this text say? Is like correctly identify the thing in this grid of pictures or whatever. All of those were used for this kind of reinforcement learning from human feedback training, right? So you would have questions like this, and then a human would tell you like, okay, yeah, the answer is correct, so you get certain rewards. So this is, if you're doing a reinforcement learning assignment, I think, for this class. So think of this as the same. Instead, the award that it gives is like, it tells you that, okay, yeah, the token that you have generated is correct, essentially. That's what LLMs do, right? So they give you, even today, if you use ChatGPT and it asks you, okay, how is the response generated by ChatGPT good or bad? There's a thumbs up and a thumbs down. That's RLHF. That's how ChatGPT improves itself, because it looks at the response that it's given, looks at what humans tell, like, oh, is this response good or is this response bad? And based on that, the model is improved or deproved, right? So eventually, like, obviously there are two phases. The first phase is you take the feedback, and the second phase is you use that feedback to maximize the model so that it always moves towards a positive feedback loop, right? So that's the three-step alignment process for a model. The first is the pre-training, then is the supervised fine-tuning, and then is the reinforcement learning based human feedback, right? These are done in sequentially, obviously, because you can't fine tune when a human is already interacting with it, right? You fine tune once the model has been fine tuned, it is essentially complete. So most of the previous thing, like this, all of this information is from 2022. All of these were generated. These generative LLMs were trained by this alignment process. End of 2022, Andrei Karpathy and many others figured out that this is not the only possible alignment process. There's a lab in China. The people who created DeepSeek came up with a much better alignment process for this as well. So their results have improved over this. So again, this is an open field, and you would have to solve it, right? So putting it all together, first we had the language models, the natural language models. Like this graph is completely, I mean, whatever the y-axis means, it doesn't mean anything. What I'm trying to tell you is that like usefulness, how useful language models became to people outside of the domain itself. So initially it was just simple language models. Then came the generative transformer model, GPT, GPT-2, which was entirely reliant on pre-training. ChatGPT brought in alignment, where it was taking the outputs of the original GPT model and aligning it perfectly to what humans were using. So that's essentially what ChatGPT is. It has the older transformer architecture that it fundamentally it still has the old transformer architecture that it was using in like 2021 under Sam Altman and OpenAI. But the alignment process has gotten much bigger. The pre-training process has gotten much more much more focused. It doesn't just look at the internet generally. It has like other things. And yeah, this is how ChatGPT came along. What's left is like we kind of understand what the best way of creating generative LLMs are. You can create an LLM on your computer, on your laptop, on your own, using like any kind of nano GPT stuff. But your smaller LLM is probably not going to perform as well as a general DeepSeek or ChatGPT or whatever. So the future for this field to use this kind of thing is targeting a single domain and making sure your model does not drift out of that domain. The way this is done is prompting, like what is the best way of prompting an LLM to generate these tokens? And the other is fine tuning. And fine tuning can be done in so many different ways that, again, like I explained. A big major problem has been that like LLM model sizes have gotten way too big, right? So a lot of modern research space in this field is how do you shrink the model sizes? How do you discard information that is not being used? Because one of the big power, one of the like major strengths of LLMs was that even if something is used, a word is used 5 times in a million word corpus, it still remembers that. There's still a neural pathway within that LLM to remember like very edge case words. So how do you keep that strength but reduce the size of the LLM? Like, do you have a better architecture than the masked self-attention transformer architecture, right? I mean, if you look at results, people are trying all sorts of different architectures and models, like things that were discarded in the 80s and 70s and 80s, where people are like, this architecture doesn't make any sense for neural networks. You'll find that people are testing those out because everyone wants what is the next step, right? We have reached, essentially, we have plateaued the performance of large language models. So what is next? What is the solution here, right? The big thing that modern people are doing is they have made LLMs multilingual and multimodal. So it is original LLMs were either English only or Mandarin only or Chinese on or Spanish only or whatever. But modern LLMs, like especially the big three, Gemini, ChatGPT, and Claude, they are all multilingual, right? So if you ask the same model a question, it gives you the correct answer, but it has essentially created its own dictionary. It has created its own corpus of meaning, a latent space where all the different words in different languages are associated with each other. Because it doesn't really, a large language model doesn't really understand language as we know it. It understands tokens and embeddings. So the embedding for different words in different languages, which mean the same thing, fall close by in a major in the latent space, right? So one of the things that LLMs have been doing for LLMs for any kind of like modern large language models is that what scientists have discovered is that if the model is truly multilingual, whatever it learns in one language, it applies that knowledge while speaking a different language. And it doesn't just have to be language, it can be any other domain as well. So like if it learns something from one application domain from medical domain, it can apply that understanding to, say, for example, chemical domain. So these are like some questions that you need to know to answer if you're telling someone, if you're telling a company that, okay, you should use LLMs to solve your problem. These are like common questions that you should have and you should be able to answer. A modern LLM speaks all these languages, right? Mandarin, English, Spanish, whatever. What language is it using internally, right? Does that question even make sense? Like, if you ask what language an LLM is using internally, it is using math, right? So does that make sense, right? A big thing about LLMs is that it looks behind, right? The self-attention mechanism tells it that it doesn't, when you ask it a question, it doesn't look at just the final word of the question. It looks at all the words that came before it as well. So another big question is that, is your LLM also looking ahead? Is it the probability distribution that it is sampling from? Is it centered on the token that is currently being generated? When a human speaks, you're not just thinking of the word that you're currently speaking, right? You have a plan that what you're talking about. Is an LLM doing this? Right. And finally, a major problem with LLMs is that you can ask an LLM to reason, right? Okay, you give an LLM a problem and it gives you an answer. And then the next question you ask is like, okay, how did you come up with this answer? So when an LLM answers that, is that answer true or is it lying? Like, is there a difference within that LLM between truth and lies? That's something that you have to solve. It's a mostly unsolved problem. So we finish up by saying like 3 different problems, right? That like you guys, computer scientists, will have to solve essentially in the future. And you have to decide whether this is even a solvable problem, right? So these examples are taken from Anthropic's Claude LLM. So you ask it a question, right? You ask it a mathematical question. And then it solves the question and gives you the answer. The answer is correct. And you ask it to reason it out, like how did it come up with the answer, and it gives you a reason. But then you give a wrong answer. Then sometimes it gives you a wrong answer, and then the reasoning that it gives you, the motivation that it gives you, is completely wrong, right? This happens because the LLM internally, it doesn't have like continuity of thought. It's not a person. It's not thinking anything, right? So what happens is that the token that it generates is what it thinks is what we want to see from it. It is the token that is generating is what a human might think is the most obvious token to be generated. That is not always accurate, right? It is sampling from a distribution. So it is lying, but it doesn't really have a concept of lying. It is just generating what it thinks is most obvious, right? So if you ask an LLM like, okay, how did you come up with an answer? The answer to that question is what you think it should say, not what actually happened. So that's something that you have to figure out how to solve as a computer scientist. The other is hallucinations. I mean, everyone knows what hallucinations are, right? You ask a question of an LLM, and it gives you an answer that doesn't make any sense. The best way to figure this out is like, even if you take a modern LLM, you tell it a somewhat obscure topic, research topic, and then you ask it for references, and it's going to generate you 10 references to papers that don't exist. Right, it's going to hallucinate because it expects that it's going to give us an answer, right? So, and modern LLMs have started solving it by taking each of those tokens, each of those generations, and putting it into Google and searching whether that paper exists or not. So there are ways of solving it. Again, these are solutions that you have to come up with. And finally, the major problem is most LLMs have like sensors, right? Like certain topics that it won't talk to you about, right? Like personal safety topics, bomb making topics, etc., hacking topics. It's not supposed to talk about those, but you can make it talk about those by just by jailbreaking, essentially, right? Because it doesn't naturally understand this kind of like sensors, right? So it has to be like all these kind of like restrictions on an LLM sits on top of the LLM. It's not a fundamental restriction within the LLM itself. So again, how do you stop this? Like this is very difficult to stop. This is essentially a cybersecurity problem where the better you get at stopping this kind of like jailbreaking, the better the jailbreakers get, essentially. So this is pretty much a cybersecurity problem that is a very open question. Like this is it's almost completely unsolved. How do you deal with this? And yeah, that's pretty much it for today's lecture. This slide is going to be up online. If you want to build your own GPT, Andrei Karpathy's web has a really good YouTube series and a really good GitHub for building your own GPT using whatever text you have. You can train it on your own Discord or Telegram or text or whatever, or WhatsApp. And you can also train it on whatever book you have, online fan fiction or whatever. You can train it and you can see what it says. It's very easy to do. That's it. And like I said, a lot of these are open questions. This is a field that is still be under development. So if you have suggestions, if you know how to fix some of these problems, you can work on it. All right. Thank you so much.